Well, hello and welcome. In this video, I'll be working through the solutions for all of the Chapter 3 test review questions. Might be beneficial to have a graphing calculator nearby as I'm going through and explaining it, just in case. But again, this is just more to describe each of the solutions. So let's go ahead and just jump on in. First question wants us to just identify the critical numbers. So critical numbers, if we recall, are just going to be, if I could actually draw on this, whenever f prime is equal to 0 or whenever f prime is an undefined value or does not exist. So if we go ahead and find f prime to start, f prime of x would just be a few power rules. So 2x cubed, 3 would multiply with the 2 to make a 6 as a coefficient, times x to the, and then the power drops by 1, so squared. Next one, 2 times 3 makes a 6 as well. Power drops by 1, so just a plain x. And then negative 12x will just be negative 12 with a plus 0 for the constant at the end. So for this one, since I'm doing the set equal to 0 step, it seems to me like the 6, and the 12, I should be able to factor a 6 out of all of those, which will make the factoring a little bit easier for the set equal to 0 step. So if I divide 6 out, my new terms would start with a 1, a 1, and a negative 2. And that does factor kind of nice. What multiplies to the negative 2 that will add to the 1. In this case, that would be an x plus a 2 and an x minus a 1. So if I now set each of those equal to 0, my two critical numbers from the first one, I would get a negative 2, and from the second one, I would get a positive 1. Hence my two critical numbers of negative 2 and 1. Now on to number 2. Number 2 wants us to determine where it's increasing or decreasing. So this is now going to still be a first derivative concept. However, I'll actually want to set up a sign line to be able to test it. So basically it starts with like identifying my critical numbers first and then setting up that sign line or number line to be able to test which ones come back positive or negative. So that's where I'm going to begin. Figure out my first derivative. In this case, the 3 would come out front, so negative 3x squared. 2 times 6, that would give me positive 12x, and then the minus 2 is a constant, so that's going to turn into 0. So at this point, it looks like I could factor out a negative 3x, and that would leave a positive x from the first term. And let's see, negative 3x times what would make positive 12x? Well, that seems like it would need to be a negative 4. So it appears my two critical numbers from that derivative will just be 0 and 4, setting each of those factors that I just found equal to 0. So I'm going to go ahead and set up a number line here with those two values from least to greatest listed out, and then test each interval. So I feel like negative 5 would do just fine for the first one, probably positive 2 for this middle one, and then maybe positive 10 for the last one. And ultimately all I have to do is plug into my derivative, because again I'm thinking slope. So it's going to probably be best to plug into that factored version there and just count negative signs. So if I did negative 5 out front, that would make that a positive number, times, and then it would be a negative number in this parentheses, so a positive times a negative should come back negative. Plugging in 2, the number out front would be negative, the number in the parentheses would be negative, so two negatives when I multiply should give me a positive result. And plugging in 10, that would give me a negative out front, but a positive in the parentheses. A negative times a positive should come back negative. So to actually answer each of these, this would be my decreasing to start, then increasing here in the middle, and then back to decreasing at the end. So as intervals, my increasing interval looks like it was just from 0 to 4. Decreasing, though, was the negative infinity until I got to 0. But also combined with this second place where it was decreasing, which would be 4 till the end of the graph or till infinity. Okay, moving on to number 3. This one's now not only trying to identify increasing and decreasing, but actually applying what that would mean if it does switch to identify things called relative extrema. So this is going to be looking for relative max or relative min, making sure that we label as such. So basically I'm looking for changes from increasing to decreasing or vice versa. So just like the last problem, we would want to start with identifying what the derivative is and see whenever it equals 0 or undefined. Here it doesn't appear as though it's going to have any undefined values, so it's really just set it equal to 0 for part A. This derivative, though, would turn into 2 times 2 in front, 4x to the power of 1, since I drop it down by 1, then minus 4 comes out of front of this one, x2, and then the new power is 1 last, so power of 3. So kind of similar to one of the earlier problems. Could factor out some stuff. They both have a 4 and an x, so take that out. That would leave me a 1 from the first term, and then minus an x squared. That I can now set each of those equal to 0 and solve. So it seems like my critical numbers for this one are going to be 0 from the 4x that's in front, and then a positive or a negative 1 from the parenthesis here. So positive 1 and negative 1. So if I go ahead and draw my number line here, that I can go ahead and test my signs of each, throw those three critical numbers from least to greatest on it, and then again we'll plug into, it looks like this will be the easiest version, and just count negative signs. So probably -5 for this first one. Don't have a lot of good options here, so negative maybe 0.5, positive 0.5 for the next one, and then positive 5. So just a whole bunch of 5s or 0.5s with positives or negatives seem like the logical one to go with. So let's go ahead and try it out. Plug in -5, the number in front of the parenthesis would be negative. The number inside the parenthesis also would be negative, so that means that would come back positive, so that would be an increasing interval. Negative 0.5, what's outside would be negative, what's inside would be positive, so that it makes a negative, which then means at this value, if it switched from increasing to decreasing, that should have created a high point on the graph, so that would be a relative max. Go ahead and move on to the next one. Plugging in positive 0.5, I'd end up with a positive out front and a positive on the inside of the parentheses, so that would be 2 positives which stay positive, which tells me since it's switched, that must be a relative minimum. If it was coming down and switched to coming up, that's definitely a low spot. And then the last one, let's say plug in 5 to test this interval. It'd be a positive out front, but then a negative in the parentheses, so that would in fact come back negative, so that gives me a second high point or relative max of this graph. So in identifying them, that's going to be a good start here. Relative max, I'll go ahead and get that part set up. It looks like I've got one ordered pair that starts with a -1 and another one that will start with +1. To get the y values, I actually plug back into the original. So if I go ahead and plug back into the original, f of, actually let's go ahead and do it underneath here, f of -1. If I plug that in, I'd end up with 2 minus 1, so that turns into +1. And if I plug in +1 for the other y value, that's going to also give me, it looks like a 2 minus a 1 for a 1. So -1, 1 and +1, 1 are my two relative max points, or extrema. And my relative min was when it was 0, and if I plug in 0, it looks like I get 0 take away 0, which stays 0. So there's my 3 relative extrema for part A. For part B, it's going to be pretty much the same approach. Start with finding the derivative of this. This one happens to be a quotient, so I'm going to have to use quotient rule. So that would be the bottom function times the derivative of the top function. So it's going to be x minus 2 times 2x minus the top function times the derivative of the bottom function, which is just 1, over whatever that bottom function is squared. So if I now go ahead and distribute things out, it looks like I get a 2x squared minus an x squared on the numerator. Actually, I'll just go ahead and show all that stuff. So 2x distributed through gives me 2x squared minus 4x. And then I have minus x squared afterwards, still over x minus 2 being squared, which I can then simplify and call that x squared minus 4x in the numerator over x minus 2 quantity squared on the bottom, which I can factor an x out of that to make the setting equal to 0 and undefined steps a little bit easier. So my critical numbers for this, kind of condensing all my space here by writing it this way, but my critical numbers look like would be 0 from the x that's from the top, a positive 4 from this x minus 4 parenthesis, and then a positive 2 from the x minus 2 that's from the bottom. So there's my 3 critical numbers. Let's go ahead and just set up a sign line with those 3 values. Least to greatest would go 0, followed by 2, followed by 4. And again, we're going to be plugging into this guy right here. So let's just maybe pick like -5 for the first interval, probably +1 for the next one, +3, and then maybe +10 just for the last one. Could go with +5. Doesn't really matter as long as I pick numbers that are on each of those intervals. So ultimately the denominator being x minus 2 squared, the denominator no matter what I plug in is going to come back positive because of the square. So it's really just what happens on top that I'm going to be caring about. So plugging in a -5, I would have a negative times a negative, which makes a positive. So overall, that whole fraction would be a positive or increasing interval. Plugging in 1, I'd have a positive times a negative on top, so that's going to come back negative. So that means I do have at 0 itself, that would be a relative max point. Next one, if I plug in 3, I'd have a positive times a negative, so that also is a negative. So let's see, that means, well, 2 is undefined anyway, so that didn't change at all. But kind of hopefully makes sense if it's an undefined value that it is possible to have back-to-back decreasing intervals. And then after that, +10 looks like I get a positive on top, and divided by positive would stay positive, so that means this must be a minimum point. So this one, instead of having 3 points, only had 2 because at 2 itself it's undefined, so I didn't really have to worry about that critical value being an extrema. But the other critical numbers did end up working out, so I had a relative max according to our sign line there at 0, comma something, and then we had a relative min at 4, comma something. And again, anytime I need a y value, it will always come from the original function. So I'm going to go back and just plug into the original guy, and let's see, if I plug in 0, I'd have 0 over -2, which stays 0. And if I plug in 4, I'd end up with, let's see, f of 4 would be 16 over 4 take away 2, so over 2. 16 over a 2, that would reduce to an 8. So 4 comma 8 should be my relative min point for that part. Moving on now to number 4. This one actually wants us to do what are called the absolute extrema. So that usually means that they're probably chopping off the arrows that potentially would be at the end. As you can see here by saying that it's a closed interval, or it starts at -1 or an x value of -1 and stops at an x value of 4. So that does definitely have potential that those two numbers, -1 and 4, that could be the highest point of the graph or even the lowest point of the graph. And then any other critical numbers that fall between those, I would have to be worried about potentially being extrema as well. So let's go ahead and see if there are any other critical numbers between those. So taking the derivative of this, I get 3x squared for the first term, minus 12 for the second term, and then plus 0 at the end. So this won't be undefined at all, but it does seem to be, since there's only a single x, I could probably just isolate, so add 12 to move that over, get 3x squared equals 12, divide the 3 off, x squared equals 4, and take a square root, and I would end up with x being positive or -2. Now -2 doesn't fall in that interval, so I really don't need to worry about that plus or minus symbol. So really my critical number, the only other number I'm going to have to do is plug in 2 as well. So now at this point, we just need to figure out what are all of the y values at these points, and whatever is the highest y value must be the max, whatever is the lowest y value must be the min. So if I plug in -1, it looks like I'd end up with -1 plus 12 plus 1. So the two -1 and positive 1s will cancel out, leaving me 12. Plugging in 2, I end up with 2 cubed is 8, minus 2 times 12, that would be 24. Plus 1, so what's that? -16 plus 1, so that would be -15. And let's see, if I go ahead and plug in 4, I'd end up with 4 cubed is 64, minus 12 times 4, so minus 48, and then add 1 to that. So that seems to me like I would do, what is that, 16, and then plus 1, so 17. So out of those values, what did I get that was the largest? Looks to me like I got the absolute max to be at the point 4 comma 17, or just having a value of 17. And then my absolute min looked like was the negative 15 value, which was at the ordered pair 2 comma negative 15. So for the test, I'm okay with you just putting it as the ordered pairs there, since it doesn't really say if it is the location or if it says is it the value. So kind of putting both down makes the most sense. At negative 1 being 12, notice that's not really the highest point, but also not necessarily the lowest point, so that's the only one that I really didn't have to worry about doing a whole lot with. All right, moving on to 5. 5 now wants us to talk about a concept called concavity. So being concave up or concave down, all of those, conceptually speaking, means I want to know what is my second derivative. So basically I'll just need to start this problem by figuring out what f double prime is, and then I'll worry about basically doing the same thing we did for increasing and decreasing. Identify the critical numbers, set up a number line, and then test. Now the other part of this problem asks for any points of inflection, so basically points of inflection are going to be, for this part, any change in concavity, but it does have to be at an actual defined point. So change of concavity. So let's go ahead and get the ball rolling, identifying that derivative I need. So f prime for this one we got to start with. So 4 times 1/2 in front would be 2x to the third. Minus 3 times 4, that would be 12x to the second. We need to go one more derivative to get to the concavity analysis. So 3 times 2, that would give me 6 in front, x to the power 1 less, so 2. And then 2 times 12, that would give me negative 24. And then x to a power of 1, so just like we've had happen a couple of times already, it looks like I can factor out a 6 as well as an x. So call that 6x times, I would have an x, and then minus 4 in the parentheses. So my two critical numbers from this derivative are going to be, looks like 0 from the front part, or the 6x portion, and then a positive 4 from the parentheses. So just like we've done before, set up a sign line. This time it's only got 2 numbers on it though, so it should be a little bit faster. And we will be doing all plugging in steps to the derivative, or sorry, the second derivative right there, and just counting the negative sign seems easiest. So negative 5 would be the number I would choose for this first one, probably 2 for the next one, and then maybe positive 10 or positive 5 for the last one. Doesn't really matter. Something bigger than 4. So if I plug in negative 5, I'd have a negative number outside, a negative inside the parentheses, so 2 negatives multiplied gives me a positive, so that must be concave up. If I plug in 2, I get a positive number out front, but then a negative number in the parentheses, so that's going to come back negative, so that's going to be concave down. And then plugging in positive 10, I get a positive in front, and then a positive in the parentheses, so that's 2 positives, which stays positive, so concave up. So it looks to me like I've got actually 2 points of inflection, because it did change at 2 different places, right? So both 0 and at 4 are going to be points of inflection because of those changes. So we can go ahead and maybe set up those ordered pairs. It would be 0 comma something and 4 comma something. I've established that it was concave up, it looks like, from negative infinity until I get to 0, but also again after I get past 4, so 4 to infinity, and then concave down there in the middle from 0 to 4. So just like before though, to get my y-intercepts, it would be plug into the original function. So if I plug in 0, I'd end up with 0 minus 0, which stays 0. And if I plug in 4, let's see, that one's going to be a little bit trickier to do mental math with. That's going to be half of 64. No, 4 to the 4th. That's actually 216, I think. Double check here. Give me a second. So 4 to the 4th, that is 256. My bad. So divided by 2, that's going to give me a 128. Then minus 4 times 4 cubed, that's also going to be 256, I believe. Yes, it is. So if I subtract that, that should give me negative 128 as my other point of inflection. So making a graph for this one would require a fairly large grid, as you can see. I'd have to go all the way down to negative 128. But anyway, there's our concavity up, concavity down. Again, the points of inflection were just defined points where it did switch. And to get the y's, just like we did any other time, we plug into the original function to get those y coordinates. All right, number 6. For this one, it wants us to set up a problem and try and figure out what a minimum is. So because the word minimum or even maximum is involved, high likelihood that I need to find a way to get a derivative involved, try and figure out when the derivative is 0 or undefined. This one is probably going to be something where it's actually equal to a value, so equal to 0. Two positive numbers. I'm just going to choose two letters, x and y. So if it says that the product of those is 192, I could just set that up and just say x times y equals 192. And then the sum of the first plus 3 times the second. So if I'm calling the first number my x and my second number my y, just to kind of get things set up straight, to do that second part, it would be the sum s. Again, I get to kind of choose. So if you'd rather use a different letter than s, more power to you. But with this one, it's going to be the sum of the first, so that's going to be just plain x plus, and then 3 times the second, so that would be 3y, must be a minimum. So basically what I'm going to try and do is take something from this first expression, isolate one of the letters, and then substitute it into the second expression. So for me, it seems like it would be easier to replace the x instead of the y. So if I go ahead and just rewrite this top one as x is equal to 192 divided by y, just to get the x by itself, I should then be able to put that in place of the x in that expression here. So let's go ahead and write what that expression would be. This would be s is equal to 192. Actually, I'm going to set this up a little bit easier. Over a y is technically the same as saying y to the negative 1. So since I'm going to need to find a derivative next, I'm just going to go ahead and get it set up in a nice and easy format to do. And then I still have the plus 3y afterwards. So let's go ahead and do that derivative. So this would turn into s prime, or we could do ds over dy if you'd rather that notation. The next term is going to be negative 192, because negative 1 moving out front, multiplying gets me that value, times y to the, and then drop by 1, so it actually becomes negative 2, and then plus 3y. Or sorry, just plain 3. So now at this point it would be, let's figure out when that equals 0 or undefined. This y to the negative 2 technically is in a denominator, so what I'm going to do is just clear out that denominator by multiplying a y squared through on both sides. So y squared times that first term just leaves me that 192 but negative. Moving it to the second term, it's actually just going to stay a y squared but in the numerator. The right side, on the other hand, turns into 0. And then from here, it's just basic algebra. Let's go ahead and subtract, or sorry, not subtract, but add that 192 over. And so that would now turn into 3y squared equals 192. Divide the 3 off. So 192 divided by 3, that's going to turn into a 64. And then take the square root, and I end up getting y is equivalent to positive or negative 8. But it did say originally 2 positive numbers, so I know it's only the positive 8. So my second number, according to this question, I've technically identified was 8. To get the first number, all I'd have to do is just plug into my x equals equation that I have right there. So it's going to be x is equal to 192 divided by 8. So if we go ahead and just figure out what that is using a calculator, it gives me that x should equal 24. So that's my first number. And at that point, we figured out what numbers that were positive, that had a product of 192, but a sum that satisfied that x plus 3y, and it made it a minimum sum for that specific part. All right, moving on to number 7. Number 7, part A, wants us to figure out what would maximize profit. Well, I don't have a profit expression, so I would need to build it. So remember, profit is equal to our revenue minus our cost. And our revenue in this case would be the demand function lowercase p times x. So really for this, it's going to be my profit is equal to the x times the lowercase p and then minus the c. So if we go ahead and just build that, this would be 36x minus 4x squared, just distributing that x through the p, or little p, function. And then it's going to be minus the cost, so since there's more than one term, I'll just group it up in a parenthesis to remind myself that I do in fact need to distribute that negative through. So that then simplifies. If we go ahead and get our profit expression to equal, let's see, I've got negative 4x squared, take away 2 more, so that's negative 6x squared. Looks like I have a positive 36x after that. and then a negative 6 at the end. So at this point, what we're going to want to do is try and figure out what would make that equal 0 if I took its derivative. So let's go ahead and actually just figure out what that derivative is. So p prime for this one is going to equal, it looks like negative 12x, and then plus 36, and then plus a 0 or minus a 0 technically at the end. So let's figure out the critical numbers of that by setting it equal to 0. It's never undefined, so I don't have to worry about that. To me, it seems like adding the 12x that way would make the most sense, just so I have positive stuff going on. So adding 12x would make that happen, and then divide by 12. We get an x value of 3. So apparently the level of production, if I could speak, would be 3 units, would technically be maximizing our profit. As for part B, this one now wants us to do an average cost per unit. So average cost per unit is actually our cost function divided by x, or divided by the number of units. So that's average cost, which is like c with a line over it, would just be equivalent to c divided by x. So if we go ahead and figure out what that would be, it would be 2x squared plus 6 over x, and if I split that into two terms, I'd have 2x squared over x is just 2x, and then 6 over x, I'm going to go ahead and just write, kind of like I did on the previous one, as like a 6 times x to the negative 1 power, just to make the derivative portion of that a little easier. So now my goal would be, let's figure out what that average cost function prime would be. So the c with a line over it prime should be equivalent to, derivative of 2x is 2, derivative of 6x to the negative 1 would make that negative 6x to the negative 2. And just like we did before, set it equal to 0. This has an x squared in the denominator, so I'm just going to multiply both sides by x squared, distributing that through. That's going to give me these two terms. So I'd have 2 times x squared for the first term, minus the 6, because the x squared and negative, or x to the negative 2 would cancel each other out, and then equals 0 times anything stays 0. So adding the 6 over, and then dividing by 2 after that, that should give me x squared being equivalent to 3. And then take a square root of that, I end up with x equaling, can't really have a negative unit, so it's going to be plus or minus, but I'll just keep the positive one. And then square root of 3 comes back like 1.7-ish. So since I can't really have decimals of units, I would go ahead and say that this would be a minimum average cost per unit at approximately 2 units. Technically it would need to be 1.7, but that's not really a thing. So just approximating to the nearest whole. In this case, 2 is technically closer than 1 if I had 1.7 be that value. So at that point, let's go ahead and just call it approximately 2 units would minimize that average cost. Moving on now to number 8. This one wants us to come up with whatever the differential for our cost is, which is called the marginal cost. Try and get it all by itself, but also figure out what would be the change in that. Oops, typo right there. That's not supposed to say revenue. That's supposed to say cost. My apologies. I'll make sure to fix that in the future. But for this one, it's going to be from 100 to 101. That's telling me basically my dx, whenever it pops up, is going to be equivalent to 1. And then my x value also happens to be the starting value, which would be 100. So if I can get the dc function and then move the dx over, I should be able to figure out what that approximate change in cost would actually be. So let's get that rocking and rolling. Take the derivative of this side with respect to x. So instead of using the c prime notation, I'm going to go ahead and bring in those differentials. So dc over dx equals 6.25x is just going to be 6.25. And then plus, let's go with 3/2 times 0.2. So that would really be, that's, I don't know, let's just do it. 0.4 times 3 divided by 2, that gets me 0.6. And then the new power is going to be 1 less than 3/2, so that would be 1/2. So to get the dx off the denominator, I'd go ahead and just multiply both sides by dx. I just have to group all of it up. That way now it is dc all by itself, and being equivalent to the 6.25 plus 0.6. I'm going to go ahead and just maybe turn this into a square root function of x, then all times dx. So now at this point I should be able to take the two values I found earlier, 100 going in place of the x, and dx turning into a 1, and just simplify. So for this one, it would be dc is equal to 6.25 plus 0.6 times the square root of 100, all times 1 on the outside, which that seems like it would just turn into 6.25 plus 6 times 10, or 0.6 times 10, which is just going to be 6. And if I add those two things together, it looks like I could just get 12.25. So apparently my cost for this change from 100 to 101 units would be approximately an increase by $12.25, utilizing this differential as a way to figure out that approximation. On now to number 9. This one wants us to identify asymptotes. So just as a good recap, vertical asymptotes are basically going to be anytime something approaches infinity or negative infinity as a value. So that's more where I'm going to look for when is the denominator equal to 0, because it does need to be at undefined values. So I'm going to go ahead and maybe just factor this right off the bat. This is 5x squared technically over what multiplies to 3 that adds to 4. That would be x plus 3 and an x plus 1. So it seems to me like the two places where I would be undefined, and if I actually did a limit as I approach those numbers, it would go to infinity or negative infinity pretty safely. So I'm just going to say that my vertical asymptotes are the two values that make the bottom 0, which are an x equals negative 3 and an x equals a negative 1. My horizontal asymptote really is probably more beneficial looking at the original, since it seems to be growing at the same, at least x rate, because they're both x squared. I'm not too worried about the 4x and the 3. In this case, it would be if I made those go to infinity or negative infinity, it really would just turn into a 5 over a 1, just because the coefficient on the bottom is a 1, which then is just equivalent to 5. So y equals 5 would be the horizontal asymptote of that graph. But again, what we're technically doing right there is we're doing the limit as x is approaching infinity of the original function f of x to be able to come up with that value of 5. Again, we just have to look at what the highest powers are. If it was a higher power on the bottom, then that just means the fraction would keep getting closer and closer to 0. If it was bigger on top, then it just wouldn't have a horizontal asymptote. In this case, it had the same degree of 2 on top and bottom, so the easiest way to do that is just figure out what the coefficients are, make a fraction, and reduce if you can. In this case, 5 over 1 just was a 5. All right, moving on to number 10. This one actually just wants us to kind of put it all together and make an actual graph of the function itself. So if we go ahead and maybe start with the easiest part, which should be the x and y intercepts. The x-intercepts are going to be whatever makes this equal 0. So I feel like factoring right at the beginning is probably going to make that a little easier to do. So taking out an x cubed from each term would leave a 4x from the first one. Actually, no, just plain 4. And then minus, let's see, I'd have one single x from the other one. So it looks like my two x-intercepts are going to be 0, 0, as well as 4, 0, because after all, those would be the two numbers that make that equivalent to 0. Y-intercept, technically I should only have one. If it's going through the origin, that should also be a y-intercept. So 0, 0 is the other key point. And as we find this info, may as well put it on our grid. So I've got one point at the origin and another one over here at 4, 0. Next thing it looks like as far as the blanks on the right are concerned, increasing, decreasing, and max and min. So all of that is here. This is all stuff to do with the first derivative, so f prime. So I'm going to go ahead and just figure out what f prime is right underneath. And it's actually easier to use the original version instead of the factored. If you wanted to use the factored, you could. You would just have to use product rule. So again, power rule with the original one. A little bit easier to do. So 3 times 4 in front, that gets me a 12. x2 now a power of 2. And then x to the 4th, that would move the 4 in front. So I've got minus 4x to the, and then the power is down by 1, so third. And that looks like it also can factor. I can take a 4 out of those two terms, as well as an x squared. It looks like that would leave a 3 from the first term, and let's see, just a negative x from the second one. So my two critical numbers for that specific derivative are going to be 0 itself and 3. So we can maybe, let's see, where can I find some space to do an analysis of that? Let's just do it right underneath that. So this is going to be A sine line was 0 and 3 on it, so should be relatively quick. So I'd plug in maybe like -5, maybe 1, and then +5, I guess would be 3 safe numbers for that. Plugging into this 4x squared, that's going to be positive no matter what I do. So it's really just what's going to happen inside this parenthesis here. So 3 minus a -5, that's going to go positive, so that's going to be increasing to start. Plugging in 1, I get a positive times a positive as well, so increasing after that. And then plugging in 5, it looks like I get a negative in that parenthesis, so decreases there. So my increasing looks like is from -infinity until I get to 0. Apparently it must flatten for just a second and then go 0 to 3, back up the page again. After 3, it looks like it starts decreasing, so from 3 to infinity, it's all decreasing for that. So if we think about what that means, that should be a high point on the graph if it was coming up and then switched to coming down. So that means at 3 comma something, I would end up having a relative max. And I didn't have any other switches like decreasing to increasing, so there are no relative min. So coming up with what that relative max is, I would go ahead and for this portion just figure out what is the function originally at 3. So if I go ahead and show that math here, or just do that math on a calculator rather, it would be 4 times 3 cubed. Then it's going to be minus 3 to the 4th. And if I simplify all that down, according to the calculator, I get 27 as its value. So 3 comma 27 is my high point. So over 1, 2, 3 up to 27 should give me a point right about there. Next part, concavity and points of inflection. That's all going to be second derivative stuff. So I might just do that over here to the left of the grid just because I feel like I got some space over there. But let's go ahead and figure out what those would be. So f double prime for this one shouldn't be too tough. The powers are slowly decreasing here. So 2 times 12, that would give me 24. X to now a power of 1. Next one, 3 times 4, that's going to give me a -12. X to the now power of 2. Just like before, it looks like I can factor a 12 out as well as an x. That would leave me a 2. And a minus x, so it looks like my 2 critical numbers for this derivative are 0 itself again, as well as 2. So another sine line was 0 and 2. Numbers I'll choose would be like -5 for that one, maybe 1 for the middle one, and +5 for the last one. But again, we're plugging into specifically the second derivative, so this part right here. Plugging in -5, I get a negative out front, a positive inside, so that's going to be negative, so it looks like that must be concave down to start. Plug in 1, I get a positive out front and a positive inside, so that's 2 positives which stay positive. And then plugging in 5, it looks like I get a positive out front but a negative inside the parentheses, so that would switch back to concave down. So since there were a couple of switches, each of those points actually at 0 and 2 are going to be points of inflection, so I can go ahead and maybe set those up as well. So I've got 0 paired with something as well as 2 paired with something. Each of those y values will come from the original function. And then the concave up and concave down, technically we have identified. So the concave up interval was starting at 0, stopping at 2, and then concave down everywhere else. So -infinity until 0. Combine that with everything from 2 to infinity. So if I go ahead and plug in 0 to the original function, I'd end up with 0 minus 0, which is 0. And let's see, if I plug in 2, I'd get 2 times 2 cubed, so 2 times 8, minus 2 to the 4th, which is 16. So that doesn't seem right. Hold on, please. So sorry, it should be 4 times 2 cubed, 8. There we go. Then minus 16, that gets me 16 itself. That makes way more sense. Having 2 that were the same height, that didn't make any logical sense for me. I knew it needed to be about halfway between those two, or at least my x-intercept and that high point, or the relative max. So to me, it seems like we have pretty much everything we need. It's going to start coming up the page. As I get to 0, it's supposed to apparently flatten. So that would be like concave down for that part as well. It then switches and starts increasing again. So now it's concave up until I get to that point right there. Then it switches its concavity, which makes some sense. It should start coming back down or decreasing in slope. So I go up to that high point, come down through my x-intercept at 4, And voila, I've been able to create a graph that looks something kind of like that. Obviously it's not perfect when it came to graphing, but as far as like the points that I'd be looking for when it comes to grading, I look to make sure your x-intercepts and y-intercepts are all in the same spot or a correct spot. Our points of inflection, technically our point of inflection also was an x-intercept, so as well as a y-intercept. So that one's kind of hard to distinguish itself, but the 2, 16 definitely can see where that point would be right there, as well as your high point. And in the end, we could look to see, is the arrow doing, at least, or are the arrows doing what it's supposed to do? Well, power of 4 should mean the arrows point the same way. A coefficient of -1 in front of that means they should both point down, so that at least agrees. But again, you could also just double check by typing the original function into a calculator and graphing it, and just seeing if what you just created on a grid at least resembles what you have on the screen. Trickiest part with that, though, is your screen on the calculator likely only goes from -10 to +10, so it really would only give you like this small snippet of a window here, so it'd be kind of hard to really tell if we're doing things right. So you might have to go into the window and actually just change to like what is the highest y, what is the lowest x, what is the biggest x, and so on and so forth. It seems like if you went down to at least -10 on the y, that would be safe, but could go a little bit further. Again, you're just trying to make sure that you have all of the graph that fits in there, and also just making sure that what information you collected off to the right actually makes sense for like how we actually can connect the points. So anyway, hopefully this has been helpful. Sorry if this sounded really rushed and whatnot, but again, this is just something where you can have a little bit more of a description than the answer key would be. So anyway, if you have follow-up questions, please just come find me before we start the test, and I'll do my best to try and clarify it. For those that have watched this, I appreciate you taking the time doing it. We'll catch you next time.